Well, welcome. Thank you for coming this morning for our seminar today. Before we get started, please be aware that we have exit signs here in case we need to leave the room on short notice. And having said that, those that are on the internet, we strongly urge you to send in your questions to the email address that's shown on the bottom of the monitor, to send them at first opportunity, so it will have sufficient time during the Q&A to take your questions. So with that, Jen?
Okay, thanks, Peter. Good morning and welcome to our seminar. It's my pleasure to introduce our speaker today, Dr. David Koch, who will talk about the air quality impacts of low vapor pressure VOCs based on chamber experiments. Dr. Koch is a professor of chemical and environmental engineering in UC Riverside. He received both his PhD and master's degree in environmental engineering science from Caltech, and his bachelor's degree in environmental engineering and chemistry from UC Riverside. He has been on the faculty at UC Riverside for, I guess, almost 17 years, since 2001. Dr. Koch's research interests include secondary organic aerosol formation, emission characterization, and aerosol-related health impacts. As you can see on the screen, actually, David has a very long title for his presentation today, which I don't think I'm going to read. But this presentation is based on results from ARB-funded research contract, which was designed to investigate the ambient evaporation rates of LVP-VOCs from both pure LVP-VOC compounds and also in consumer products, and also conducting environmental chamber experiments to explore ozone and secondary organic aerosol formation from those compounds. The results will help ARB to estimate the emissions of LVP-VOCs and their potential impacts on air quality. Without further ado, let's welcome Dr. Koch.
Thank you, Jen. We good? All right. So thank you. So today I'm going to be talking about the project that I worked with ARB on, with low vapor pressure VOCs. I don't really feel like reading that title either, so we're in agreement on there. But essentially, let me just go ahead and get into what the basic objectives here were. The first one was to evaluate the evaporation rate of these specific low vapor pressure volatile organic compounds in pure form and as part of some mixtures, as they are used in consumer products. It was to study the ozone and SOA formation of select LVPs and apply the experimental data to the SAPRAC 2011 mechanism to evaluate ozone formation, as well as compare ozone and SOA with the individual compounds and the mixtures, and explore not only the consumer products, but also the solvent mixtures themselves. Let me just get right into this. So, real quick, I don't think I really need to tell Air Resources Board this, but VOC plus NOx plus sunlight makes ozone. Still, ozone's a concern. This is taken off the South Coast AQMD website, showing the number of exceedances and basin days exceeding the current 2015 ozone standard. This last year we hit 132. I put the asterisk just like South Coast did. They're still working on verifying the preliminary data. But essentially, ozone is still a major concern, and VOCs can include some of these LVP-VOCs should they be able to get to the atmosphere. From the aerosol perspective, certainly you got a mixture of primary emissions from a lot of different sources, fuel, industry, fires, giving you primary organic aerosol, but the same VOC type of emissions that affect the ozone can also combine through a lot of chemistry. That's too easy to read there, to form ozone, but also form other oxidation products that can condense or nucleate and form secondary organic aerosol. So in this case, we're going to be talking about both ozone and SOA. The basic reasons here, they got to put the required slides here, right? It's human health. Fine particulate matter has different impacts on human health, as does ozone. gets into the system, causes all sorts of a whole myriad of different health effects that we're all concerned about. But again, when we talk about this fine particulate, we talk about the ozone, it has to start with the VOCs and NOx that are in the atmosphere. And this project was looking specifically at the LVP-VOCs in there. And, you know, there's a nice pretty day down home and not so nice. All right. We know that there's a gap between model prediction of ozone and also fine PM formation. There's a lot of potential reasons for the gap, but still incomplete understanding of different chemical mechanisms. It could be incomplete inventory. It could be how we handle the transport. There's a lot of different pieces that can be affecting what the discrepancy in ozone and fine PM formation. In this project, we're really looking at LVP-VOCs as a class that hasn't really been looked at a whole lot because of regulatory exemptions for VOC. So when we talk about LVP-VOCs, what are we talking about? Talking about high boiling point compounds with that have low vapor pressure, less than 0.1 millimeters of mercury, and greater than or equal to 12 carbon atoms. The actual definition LVP-VOC varies by agency. So here, standing at ARB, I should say boiling point 216. If I was over at the EU, I'd say 250. But regardless, these are some of the compounds that evaporate slowly and have fairly high boiling points. More recently, there was a white paper put out by EQMD, Vo and Morris, that challenged whether these LVP-VOCs should be really looked at as low enough vapor pressure to be ignored for their emissions. So with this, you can picture a lot of different consumer products that may have these compounds that we say, because they have high boiling point, aren't important. But after all, when we look at some of them, they may be able to get to the atmosphere. What did we study here? I promise you I don't have too many slides that are this busy. But I wanted to list all the different chemicals that we looked at. So we have a variety of compounds ranging from propylene glycol on the small side up to N-heptadecane on the larger side, various boiling points of species here, different vapor pressures. These are all defined as LVP-VOCs. I also have listed next to them in C-star space for anyone that really likes the volatility basis set. Regardless, this list of compounds was created by a number of meetings with ARB, with industry, and UCR in identifying which chemicals were being used out there in the consumer products and had a variety of different molecular structures. We also were chosen to look at 5 different consumer products. In this case, laundry detergent, general purpose spray cleaner, caulk remover, paint stripper gel, and hand lotion. I put the formulations up there. These are what we'd have to call extra generic formulations. There's proprietary information involved with the actual making of a true laundry detergent for sale. We had feedback from the industry on what would be appropriate mixtures to simulate what these different products might look like. We were also asked to look at some of the hydrocarbon solvents. So we looked at isopar-M, it's a low aromatic mixture of alkanes, isoalkanes, and cycloalkanes. Conisol C200, which is a low aromatic mixture of cycloparaffinic and isoparaffinic hydrocarbons, and aromatic 200, which are predominantly aromatic compounds. So the first part of the project was we wanted to figure out, do these chemicals actually evaporate? Because if they don't evaporate, there's really not a whole point in going a whole lot further. All right. So what we did is we built these evaporation chambers, seen here on the left-hand side. We had a number of them where we flow purified air through the system. We exchange the air 3.5 times per hour. And we put inside here, in the little Petri dishes, individual LVP-VOCs. And all we did is we measured how much we put in there to start, and then we measured the next day how much was left, the day after, the week after, the month after. Some of these went on for quite a while. Before I put that up there, I also wanted to go ahead and mention from my world, the SOA world, where a lot of these chemicals that we're going to be talking about fall. So some of you may be familiar with the volatility basis set forth by O'Donoghue, but essentially what he's done is he's looked at plotting a C star, which is a measure of the vapor pressure, for a variety of different compounds and classify things as VOCs, IVOC for intermediate volatile organic compound, SVOC, semi-volatile organic compound, low vapor organic compound, and extra low vapor pressure organic compound. And the reason I put this up here is I've been asked, and I've shown some of this work, where does this fall from a gas particle partitioning perspective? I want to stress as I put this up here that this gas particle partitioning perspective is from whether the chemical, if it's a gas, really wants to condense onto an organic aerosol. This does not necessarily tell me, looking at this system, with some of these chemicals being over by the over by the VOC edge of the band, that they are truly that volatile. Because when they are in a mixture or when they're in a big product, you have a whole lot more organic mass. That shifts where these bins are. I really wanted to specify in both my world of SOA as well as in the regulatory world of LVP-VOC, what we're looking at. So this is what the chemicals did. We put in glycerol, triethanol, amine, and methyl palmitate, and nothing happened. And I called up ARB, and we talked to industry, and we said, this stuff's not going anywhere fast, and we didn't look at those compounds any further in the study. Then, showing here all the other different LVP-VOCs that we measured, their starting weight, and the amount of time we waited for them to evaporate. So some of these compounds evaporated in the matter of a few days. All right, some of them took about a year until we got rid of them. All right, so we do have a variety, but all the chemicals that I'm going to talk about for the rest of this study are all able to evaporate under this evaporation chamber. So removing the 3 chemicals that didn't do anything, this again shows you on the volatility side of things what C stars we're looking at. So a range of between 10 to the 4 to 10 to the 6. Again, from an SOA modeling perspective, these want to be gases. From an evaporation perspective, again, we saw that some of this stuff took a year to evaporate. So the next thing we did is we took a plot. This is one of those semi-empirical type relationships where we applied evaporation rate, grams per day, versus a combination of molecular weight and vapor pressure and an empirical constant for all the different species that we investigated. And if you look here, you can see that this empirical relationship holds fairly well over the whole range of species that we studied. There's different chemical properties in there, right? Some have ether, some were glycol ethers, some OHs. Regardless, we were able to use the molecular weight and vapor pressure to estimate an evaporation rate relative to one another. So we were pretty happy in seeing this. Essentially what we're looking at when we're talking about evaporation is, if we're going to look at some kind of ideal compound or mixture of compounds, you can describe the equilibrium with the vapor pressure and an ideality constant if it's a high enough concentration, a mole fraction, an activity, and the saturation vapor pressure. And if you use this model as itself, it helps you identify how different products should be going between the gas and the particle. But then the question was asked, well, what about mixtures? Because it's interesting that all those individual species were evaporating, but what happens when we start looking at mixtures? The first issue we had with the mixture is we can't just do it by weighing. Because if we have a mixture and we're measuring by weight loss, we don't know which chemical is being lost at which rate. So what we did is we took the same evaporation chamber, we put a 200 microliter mixture into the system. This could be a consumer product or a hydrocarbon consumer product. We flowed the air, and we took it into a selected ion flow tube mass spectrometer. What this did is it allowed us to monitor in real time what the concentration of the species was that was evaporating that we were interested in. So we figured it out for an individual. We knew exactly where to look for on this system. We got it calibrated, and then we looked for the LVP that would evaporate out of the mixture. But then we had a little bit of a problem. A student came up to me and said, well, how much consumer product should we put in there? I said, oh, put in the same amount as the LVP. And my student said, well, I'm not sure what that means. Do we match the volume of LVP that we put in there? Or do we match the volume of consumer product to the volume of LVP? I thought, gee, that's an interesting question. So I asked her to go to the system and put in lots of different volumes of LVP-VOC. These are individual species, and measure the concentration as it's coming out of the, as it's measured by the mass spectrometer. And what we noticed here is that the volume of LVP-VOC was also controlling the concentration that we were getting out of the system, which wasn't necessarily a good thing to us because we had looked at the system from this equilibrium picture shown here on the right. And now we realized we had to have some sort of mass transfer limitation governing the evaporation rate as well. So shown on the left is just a simple little model of a system that's been mass transfer limited in its ability to get the concentration up into the equilibrium regime. So then the question is, well, what's limiting this? There was a discussion that we had back and forth with ARB staff. Well, it could be the viscosity of the solution, helping basically preventing the LVP-VOC from migrating out and becoming present. Or it could be something with the boundary in the interface, the amount of surface area with the air. What we saw here is we took a look at a quick model for viscosity to see if that was the limiting factor. We took the Stokes-Einstein relationship for diffusivity. We were able to get a time scale for diffusion in our system. We looked at the thickness that we had to diffuse through, and we looked on the scale that we were working at, which was tens to hundreds of days. And on that scale, diffusion didn't really matter. So we knew that viscosity was not limiting the ability of the LVP-VOC to get to the air, which left us the other possibility, which is just the actual contact area between the LVP-VOC and the air. So we ran two sets of experiments then. On the left-hand side, we ran when the volume of the LVP equaled that of the consumer product. Shown here, sorry, there's my arrow, is something like a pure compound, so this would be dB5, compared to the concentration that we would get from the caulk remover that contains the dB5, or the paint stripper that contains dB5. And again, this is for volume of LVP equaling the volume of consumer product. Similarly down here, we saw results where the general purpose cleaner was lower, as well as the laundry detergent, although we'll notice here that it's not the laundry detergent. The laundry detergent actually took off. The lotion didn't do a whole lot. On the right-hand side, we have the volume of the LVP equaling the volume of the LVP in the consumer product. So we have the same amount of LVP now present in both. And we get a slightly different picture. At the end of the day, probably the most interesting one here was this propylene glycol, where again, the laundry detergent acted very differently than the lotion did. And we believe that to be due to the fact that when we looked at the recipe that we used with the LVPs that we used, we were actually cross-linking the LVP-VOC. So while that ingredient was present officially in the mixture, it had nothing like the vapor pressure that we would expect to have. So that's the work with the evaporation side. Then we took this to our atmospheric chamber. So this is a schematic of the UCRC chamber facility. We have dual chambers available to us. We have black lights that we use to photolyze the NO2, drive the photochemistry. And then we have a lot of equipment that surrounds the system. Each chamber is 90 cubic meters in size, and they are all in an insulated larger enclosure which is flushed with purified air. This larger enclosure allows us to control the temperature as well as minimize any kind of contamination from getting into our chamber system. The temperature control we have is 5 to 45 C. We ran all of these at 27 C. We do have the ability for humidity control. These experiments were conducted under dry conditions. The way we typically ran the system is we added a little bit of NOx, we added a surrogate to the system, and then we mixed between the two chambers so that we had the same exact hydrocarbon mixture. We had the same amount of NO. We added H2O2, I'll talk about that later, as needed. And then to one side of the chamber, we added the LVP-VOC mixture. The other side was always a control. This just reiterates the type of tools that we had. We had a lot of different tools looking at the gas phase chemistry and looking at the particle phase chemistry and the particle phase mass and characterization. The surrogate that I mentioned, we basically used, probably not surprising to those of you that have worked with us for a while, we used the Bill Carter's ROG surrogate. In this case, we use what he calls a simplified ROG surrogate to mimic the total atmospheric reactivity. And here we use 7 compounds: N-butane, N-octane, ethylene, propylene, trans-2-butene, toluene, and M-xylene. Toluene and M-xylene are aromatics. We know that they do form a little bit of aerosol, but we will show that the amount of its contribution was minimal compared to the systems that we really look at. As far as the tools go, we did look at the volatility of the particles once we made them. We're starting with low vapor pressure species. We were curious, well, how volatile are the particles if they are made? So we essentially looked and saw what fraction of it evaporated at 100 degrees C. We used an aerosol particle mass analyzer coupled with an SMPS. This tool allowed us to measure the density of the aerosol that we had so that everything we report to you is in mass concentration, not volume concentration with an assumed density. So we're measuring a true mass in the system. We used a high-resolution time-of-flight aerosol mass spectrometer. Here we were looking at bulk chemical characteristics, the O to C, the H to C, etc. So one question that we were asked at the outset, because there was a lot of work coming out from a number of different groups about semi-volatile gases sticking to chamber walls. We were asked, well, if you're using an LVP-VOC, which we consider right now regulatorily as not even being able to evaporate to the atmosphere, are they going to go to the chamber surface? So we ran several different experiments where we put different chemicals into the system, and sure enough, the LVP-VOCs just sat there. That gave us some comfort that at least we weren't losing a whole bunch of this to the wall. We had good mass balance recovery, so we have the appropriate concentration for what was injected into the system. So we basically then said, at least as far as the LVP-VOCs themselves, we don't have to worry about wall losses of the gas phase species. That doesn't speak to the oxidation products, only to the starting species. So let's talk about what some of the results look like. Ozone, so we'll start with the ozone. So here's a slide that shows a whole mixture, a whole myriad of different experimental results. I want to point immediately, well, first of all, I should point out this ozone concentration versus radiation time. And shown here is a surrogate mixture. So the surrogate is the base reactivity. It's that 7-component mix that we run all the time. All the LVPs were then added one by one to the surrogate mixture, and we again looked at the ozone formation. In some cases, like DEGEE, we saw enhanced ozone formation over that of the base mixture. In other cases, like benzyl alcohol, we saw suppressed ozone formation occurring relative to the base mixture. Now, color here. That show it? Sorry, did the arrow come out? Okay, good. So in this case, about half of them were a little bit lower, about half were a little bit higher. But you have to keep in mind that the LVP-VOCs themselves are interacting with the mixture and changing the ozone formation of the 7 species that are also present in the system. So what we are looking at here when we see some of these changes in the ozone is that the LVP-VOC may be having changes in the radical concentrations by suppressing the amount of OH radical present. If we don't have the OH radical, some of the other species aren't going to form as much ozone. By changing the amount of NOx available, that's normally seen by the change in the plateau, or other types of effects with the reactivity of the mix. Now, the first thing we looked at then said, okay, well, this is interesting. We are looking at some suppression for the ozone formation with some, increase on the other. We've been showing that for decades from UCR. But if the hypothesis is that it's just a simple loss of the reactivity by not having enough radicals present, what happens if we goose up the system a little bit? We add H2O2 to essentially replace the OH being lost to the LVP-VOC. So this is a new set of experiments here. Again, you can see the surrogate right there. And what we were looking to see is whether we saw what kind of impacts we saw in the ozone formation. Now, naturally, when we look at the system, a lot of us like to look on this side for what the final ozone is. But we should also be looking at the ozone formation rate itself that gets affected. So if I go back here, you can see that there's a scatter on the lower left-hand corner. Apologize, there it is. In the rate of ozone formation, the rate of ozone formation is normally affected by the amount of hydroxyl. And then here, when we went ahead and put the H2O2 into the system, the rates themselves were much more similar. So you can see that we were replacing the loss of OH due to the LVP-VOC. However, there's still effects on NOx and other things ongoing that's affecting the total ozone being formed. Looking at this from just a couple different chemicals perspective here, instead of the whole mix, again, we can see the H2O2 effects, where if you have H2O2, they're the closed circles. Each species has its own color. If you don't have the H2O2, they're the open circles. And you can see what some of the effects are in the ozone formation. Primarily here, you can see that our closed system is forming ozone more rapidly because the hydroxyl is present much earlier in the system. At the end of the day, the total aerosol formation is not being impacted all that much, but that has to do also with the interplay with NOx. So then what we did is we said, okay, well, we better go take this to the SAPRAC chemical mechanism and see, is the data that we're seeing here looking like what we would have predicted for you before we did this, based on the SAPRAC chemical mechanism, where that's now going to account for lots of different pieces. And essentially shown here, and I could have shown this for about any different chemical, we were able to accurately model the amount of basically the ozone formation that's occurring in the system, which meant that the gas phase chemistry, as we knew it for the ozone, was probably okay for the LVP-VOCs. We didn't see any reason to come back and say, hey, one of these chemicals is far more reactive or is far less reactive. We also looked at the ozone formation with consumer products. This is, I am sure, the first time anyone's ever put a consumer product into an environmental chamber. And so that was one little challenge we had in figuring out how to even get it into the system. But shown here again, we have the surrogate in the same color. So again, you can see the surrogate kind of going through here. And we have the ozone formation that's occurring from all the different consumer products that we injected. Again, you can see some variation in the ozone being formed. If we add the H2O2 into the system, we find that again, the rate, the beginning looks much more similar. And we can also see here that if we look at a couple specific consumer products, in this case, we're taking out lotion and laundry detergent, because both of which have propylene glycol, we can compare that to the propylene glycol curve that we have, and we can see that in some cases the consumer product has some other ozone-forming species that other than the LVP-VOC contributing to the formation. I should note in here that these experiments were done so that the concentration of propylene glycol was matched to that would be present when the consumer product was in. We looked at ozone formation from select hydrocarbon solvents. In this case, all the hydrocarbon solvents, not surprisingly really, suppress the ozone formation. Again, what they're doing is they're taking the reactivity of the system, they're lowering it from the surrogate mixture that we have. I want you looking at this and saying that, or thinking that these hydrocarbon mixtures, I see it changed already, are actually depleting ozone. All right, that's not what's happening here. It's depleting the amount of OH that's available. We can see in the lower left-hand side here again that as we put in the different hydrocarbon solvents, that we were struggling to form the OH by the fact that the ozone's not increasing as fast. So we added H2O2. When we added H2O2, we actually got what we were looking for in the first place by adding H2O2 to the system. We got the reactivity back. So again, the lower left-hand corner, the slope looks about the same. And now you can see that the ozone formation itself is not being suppressed nearly as much now that the OH is not being removed by the hydrocarbon solvent. All right. So that's the ozone data. We also looked at SOA formation from individuals and mixtures. So in this case, I'm going to kind of go through it the same way, where we look at select LVP-VOCs and a surrogate and NOx. In this system here, you can see that surrogate is very low in its aerosol formation. So the amount of aromatic species in there are not forming much aerosol at the concentrations that we have. Okay? And then shown is the range of SOA formation seen for various compounds. Now, when I went into this, I expected all of these things, if I were able to get them into the chamber, they're already starting with a low vapor pressure, that they would all form a lot of aerosol. I was incorrect. N-heptadecane did a good job. So NC17 was our winner in forming the most aerosol, benzyl alcohol, DGBE. But some of these chemicals down here really did a whole lot of nothing in the system where we just added the LVP to the surrogate and NOx. But we knew from the ozone data that we couldn't just do that because some of the OH was being scrubbed by the LVP-VOCs. So we added H2O2 to the system. Oh, I don't know where that slide went. My apologies. Oh, no, this has H2O2. Just didn't show it on my title. Yeah, so we added H2O2 to the system. And in here, now we can see that more of the species are forming measurable amounts of SOA. Some still aren't. DBE5 and propylene glycol were absolute duds for us in forming SOA in our chambers. But we can see benzyl alcohols actually moved into the #1 slot, and heptadecane's up there. And some of the other species are now starting to form more aerosol. And this is likely, well, we know, I should say likely, it is due to the fact that the H2O2 is now present, and it's allowing us to consume more of the LVP-VOC. If we look at this for one chemical, just for a different perspective, so it's just a little bit cleaner, DEGEE, again, you can see the surrogate NOx down at the bottom. Didn't form much aerosol. DEG plus NO didn't do a whole lot. If we did add DEG surrogate and NOx, now we start to see some aerosol formation. Okay, if we add H2O2, that increases even further. So the reason that I'm showing you this, and I apologize for not starting it slightly different here, is the classic SOA formation experiment. It would be DEGEE plus NO, where you take a single chemical, you add NOx, you turn the lights on, and you see what happens. For this study, we were using a surrogate mixture to control the reactivity of the system. We were doing that for the ozone, but also so that we had the right reactive mixture. And you can see that if we at least have the reactivity present, we do see a difference in the aerosol formation. It is enhanced. But then we need some tool to be able to normalize, well, what's really going on here? How much aerosol are we really producing for the amount of hydrocarbon reacted? So what we did is we used an aerosol yield model, where essentially if you look at aerosol yield on the left-hand side of the axis and the amount of organic material present you will see that the yield itself will vary as you change the organic aerosol concentration. Now, within the scope of this project, we couldn't run enough experiments to possibly fit this curve for all the different data. So rather, what we did here is we still use the yield to provide some perspective on the fractional contribution of the different species to aerosol formation. What this is going to do is it's going to allow me on the next slide to compare it to aromatics, which is a natural question. Well, where does this lie? You can see that many of the yields are actually fairly small in the system. A couple of them were in the 0.2 to 0.5 range. For comparison, this is what an aromatic system would look like. This is just a bunch of aromatic data. We collected this from a different program that ARB funded a few years ago. And it shows the aerosol yield versus the amount of organic mass. And you can see that aromatic species form with atmospherically relevant concentrations about 0.05, 5%, out at these aerosol mass concentrations about 20%. The aromatics themselves tend to have a higher yield than most of the LVPs we studied, with the exceptions that we've noted, the benzyl alcohol, the NC17. Then what we did is we added H2O2 to the system. Because we said, okay, well, we're still a little short on the reactivity. We're still not forming enough hydroxyl to get this to consume. So shown here is everything. The closed symbols are when we add the H2O2. The open symbols were without the H2O2. Essentially what we saw is in all cases where LVP-VOC formed aerosol, the H2O2 enhanced it. We expected that because more of the LVP-VOC is being consumed. In comparison, just doing a little parity chart for the amount of SOA formed with the H2O2, added or not added, you can see here that, again, in all cases, we lie on the upper left-hand side of the chart. The H2O2 was enhancing the amount of SOA formation. But then the question is, now those are the individual species. What about the consumer products? So we put some consumer products in the chamber. Again, we were a little scared doing that, but we said, all right, we'll do it. Into the chambers, and we studied to see how much aerosol was being formed. So we have our laundry detergent and spray cleaner forming a fair amount of aerosol, our paint stripper, not quite as much, caulk remover, not doing a whole lot of anything for us. In comparison, we can go ahead and plot something like laundry detergent, whose LVP-VOC main ingredient is propylene glycol, on the same chart as the propylene glycol itself. We can do the same thing for lotion. Actually, we did not put propylene glycol in this one yet, did we? I am sorry. It's got to be coming. I'm getting ahead of myself. I'm that excited. On this slide here, basically we put in two different consumer products, both of whose main component is an LVP-VOC, and both of it is propylene glycol. And you can see that the aerosol formation was very different for the two systems. That was my key point for that one. Shown here, we can then go ahead and look at the SOA formation where we put the single compound along with the consumer product. So laundry detergent is up here. Propylene glycol is down here. General purpose spray cleaner had DEGBE in it. Its aerosol formation looked a whole lot closer to the LVP that was present. Paint stripper has DBE5. For all these experiments, the same amount of LVP-VOC is present, which tells us that there's some more complexities in here. There's other compounds inside these products that are driving the SOA formation for some of these systems, and particularly the laundry detergents. You also note the lotion is still stuck down here. Lotion was a funny product. Again, the LVP was cross-linked. It was a mess. And it didn't seem to do a whole lot once it was in lotion form compared to the pure LVP. I just told you. All right. We also looked at the hydrocarbon solvents to see what they would do. So shown here is a surrogate at the bottom, again, for your base case, and the amount of aerosol being produced from aromatic 200, Conisol C200, and isopar. We have two versions of Conisol C200 that we used in the study. They came from different, completely different batches. They were generated completely different. One of them, the Conisol C200 was bought as pure Conisol C200. It took us a while to get the delivery of that compound. The other one, we mixed Conisol C70 with C400 so we would have the appropriate viscosity to form C200. Okay. Regardless, these hydrocarbon solvents were all capable of making aerosol. The C17, C13 bands are put on here for comparison for the aerosol formation. Just keep in mind that we're talking about similar type of species here with the Conisol and the isopar. We juiced the system up with H2O2. Aromatics were much happier then because the aromatics were eating up all the OH again. So now our aromatic 200 sort of soared to the biggest numbers that we saw as part of the study. It took us a while to clean our chamber, honestly, after running the aromatic 200. Again, you can see the C17 and the C13 band. Really what's happened here is the aromatics have taken off. But probably what would be one of the more important takeaways here is the cycloalkanes and alkanes, the isoparaffins, all these are forming aerosol at reasonable amounts of quantities. And these are ones we normally have tended to ignore looking at some of the SOA formation. In closing, there's one other little thing I want to mention that we did as part of the study is we tried to look at what the relationship of the SOA formation was to some different chemical structures for the glycol ethers. We actually had a couple glycol ethers as part of the program. We saw that their aerosol formation was quite a bit different than one another, even though they were fairly similar for starting vapor pressures and starting molecular weights. So what we did is we found a series of ethers, the glycol ethers, and other types of ethers. And you can see them shown here, where we tried to basically change the spacing between the ether and the hydroxyl group, the ether and the methyl group. We changed the amount of branching present to see if we could understand what was actually helping drive the aerosol formation, because it was quite a bit different for the two glycol ethers we studied. What we found, essentially, if we actually plot our different species here, is that the SOA formation was really associated with the presence and location of the OH group itself, that the OH was very important for the SOA formation. The ethers that had the OCH2CH2 with two of them, OH structure, were the ones that actually dominated the aerosol formation. And again, the SOA fractional yields that we see is also going to be dependent on the amount of VOC that reacted. Having said that, I'm just going to put up the quick summary, and then we can open up for whatever questions that there are. We found the UCR chambers were suitable to meet the goals of the study for ozone and SOA formation. The LVP-VOCs were stable. The experiments were repeatable when we did the repeat experiments. Most LVP-VOCs that we studied evaporated in less than 6 months time frame. There were a few that I identified that did not, that had extremely low vapor pressure to begin with. We used SAPRAC 11 to evaluate the LVP-VOC studied. We found that it was doing a good job. So we're not really recommending any big changes for ozone formation from the LVP-VOC studied. The hypothesis that the LVP-VOCs, because they begin with such low vapor pressure, form lots of aerosol, was proven to be generally not true. Some of the chemicals formed a decent amount up where aromatics do. Most did not. The chemical structure was found to be a significant driver of SOA formation. Again, we saw the presence of the OH as well as the distance between the O and the OH were major drivers for the SOA formation. The lab created generic consumer products. Again, we created them in the lab. These were not consumer products. These were mixtures where we followed the recipe from the Consumer Products Association. Had a weak influence on the ozone formation compared to the surrogate mixture, but did have a strong impact on the SOA formation. And we could not explain this solely based on the pure LVP-VOCs in there. Again, remind you of the propylene glycol results. Hydrocarbon solvents formed appreciable amounts of SOA. All three of them did. Aromatics 200 with sufficient OH was the champion there. SOA and ozone formation from photooxidation. We did look at SOA and ozone formation from photooxidation of other classes of LVP-VOCs. We saw when we did the evaporation study that while we had a wonderful trend, we know that it looks like we can be telling you molecular weight times vapor pressure is a great measure for the ability for the chemical to evaporate. The actual magnitude of the evaporation was being mass transfer limited. We could do it all over again. Right? We had to wait 400 days to do the first one. We would actually change the way that we did that evaporation study to match the surface area air interface as opposed to a volume. The HO2, let's see. I'm sorry. I'm telling you what I'm doing. And now again in my future work. The future work, all right? I'm not changing anything I said. We still need to look at SOA and ozone formation of other classes of LVP-VOCs. We did some in here. We did some extra ones. I showed you at the end. There's many types of LVP-VOCs. Evaporation study, we really have to understand the mass transfer kinetic limitations. Like I said, I would actually change how we looked at the evaporation in the evaporation chambers to get a better handle on the system. We need to be able to predict the effect of reactivity in the atmosphere. Certainly whether you are in an urban area or downwind will change the amount of HO2 and NO present, which can have large impacts on SOA formation. And then, a detailed study about SOA formation as a function of the different molecular components, the chain length and branching, is really necessary if we're going to provide guidance on all the general LVP-VOCs out there. The glycol ethers, we could see how the glycol ether acted very differently depending on the presence and location of that OH. Similar types of studies really need to be out there for some of the other classes. And I'd be remiss without mentioning that there's future work that we still need to look at with the vapor and particle wall loss in the chambers. These are ongoing challenges with all SOA and experiments. And I just mentioned that that's something that we should continue to look at, even though the LVP-VOCs themselves appear to be stable. That obviously acknowledge ARB here for their support in this work. NSF helped with some of the structural studies with the glycol ethers, where we went a little bit on a tangent, and the Keck Foundation for its support in a lot of the instrumentation that we have.
Thanks very much, David. Before I open the question to the room, I do have one question from the webinar audience. I'll just give to you to read it, David.
Sure. Dear presenter, I think you may consider measuring the surface tension of all mixtures to elucidate the relationship of a compound and mixture, i.e. the product, on its vapor pressure. Surfactants in solution most commonly will nonlinearly increase the vapor pressure of a pure compound because the surface tension is reduced, effectively allowing for an increase in free energy and a reduced barrier at the surface, such that molecules may more easily escape from the bulk solution. So I thank the audience member for that question. In this case, the way we were looking at our evaporation relationship, we had a fairly large droplet where we don't expect to have the same kind of surface tension of impacts that we typically have when we're looking at the aerosol and its gas particle equilibrium. So in this case, this is a very interesting question for what kind of impact it might have on the gas particle equilibrium. But when we're looking at the evaporation of the pure species, this is likely to be a lesser effect in what we've seen. I have another question. It's weird to get a question there because I can't interact with the person. Maybe you'll give me a follow-up.
I think from the beginning of your presentation, you also talk about the gap between the model and the reality. And based on your result, do you think what's your suggestion for the future emission inventory, especially for those compounds, to make those gaps smaller?
Well, right now they're not included at all. All right, they're exempt. From an SOA perspective, some of them that we measured clearly can contribute. We have to look at the total inventories for the total emissions that are actually going up there before I can really comment on what impact it will have. I do believe that it's important that we've looked at the LVP-VOCs. I don't think we can rule them out as a totally unimportant class because they are evaporating, they are gained to the atmosphere, so they should be contributing. But the extent requires the other multiplier, which is the total inventory for release, which is probably underestimated because we assume it doesn't.
All right.
Is that what you want to know, or?
Oh, because emission inventory, basically is a very, very tedious work, we know, okay? And we learned a lot of experience in the past. And however, we constantly saw the prediction and the reality always has a gap. And emission can be the major issue, even though the mechanism, okay, based on the academic study, there's a lot of progress. But the emission inventory is still, from our perspective, is very difficult, especially those compounds. And there's a lot of information we need to get together, make emission inventory most become real. Yeah.
Right. Yeah. No, I would definitely agree with you because there's a lot of challenges. Because just because we have the LVP-VOC present doesn't mean that's going to necessarily get to the atmosphere. Especially, I mean, even here, I showed you how long it took for some of the individual species. I know ARB funded a companion project here, which was looking at the ability to go down the drain versus getting to the atmosphere. So there's a lot of different questions for where the final fate of that compound is going to be. What I'm hoping you got out here from the evaporation side is at least a band idea of which LVP-VOCs may be getting to the atmosphere and how you might be able to relatively look between those two. But certainly when we think of how we use many of our consumer products, I don't leave my consumer products in an open Petri dish for 6 months either. And I think that's one of the big challenges in the inventory. So I would agree with you. That's a big part of the big difficulty.
Thank you, Dr. Cocker. Had a clarification to make and then a question. I wanted to mention that our emission inventories do include LVP-VOCs, and so hopefully those are also modeled when we do our modeling work. The clarifying question was, could you please speak to the difference between ozone suppression and ozone depletion? Because you had mentioned in the presentation that you were not saying that ozone was being depleted.
Okay, let me be. When I was speaking about any of the changes well, first of all, thank you for the clarification. Yes, and actually we did an inventory study with you guys where we classified some of the LVP-VOCs that do get out there. I was thinking more from the regulated side for VOC standards. I apologize and thank you for that clarification. I I realize how you took one of the words there. In all cases here, I was talking about ozone suppression. This is all tropospheric ozone suppression due to the fact that if we don't have the hydroxyl available to react with the different surrogate VOCs, or if we have if some of our NOx is being actually taken up by the LVP-VOCs, it can have an impact on ozone, leading to it appearing to be suppressed. However, when you take that to the actual atmosphere, the LVP-VOC is not at high enough concentration to govern the atmospheric chemistry. So the suppression effect due to stealing those hydroxyls, due to possibly pulling some of the NOx, is not present.
Thank you.
Yes. All right, do these results have any implications in terms of how LVP-VOCs should be managed by air quality agencies? I know I was asked not to put that in the report because you generally don't, I don't know. I'm sorry, I'm looking at, do you want my opinion on that one?
Well, yeah, maybe
Okay.
in general sense, I guess.
In a general sense, because yes, because I can't speak to how the regulatory agencies should really handle this. So what implications does this have in terms of how LVP-VOC should be managed by air quality agencies? Well, certainly taking the assumption that LVP-VOCs are not part of your VOC inventory, when I say this, when you're talking about product formulation and giving it exemptions, we need to be very, very careful because it looks like the boundary for what compounds are available or what chemicals are available to get to the atmosphere is further down a lower vapor pressure than is currently being used by the regulatory agencies. So that would be one implication that comes out is that the threshold of 0.1 millimeter mercury, being less than, or for the boiling point, is not really sufficient to ensure that the chemicals are not getting into the atmosphere. Other parts of the results indicate that for select LVP-VOCs, they can be contributors to SOA formation should they get into the atmosphere. That's something that should be considered. But it also shows that not all LVP-VOCs that get to the atmosphere are going to form aerosol. So in there, selectively identifying which chemicals could be having an impact are there. As far as the regulatory for the ozone, the results imply that when we use this larger chamber and really control for the losses and some of the other effects, we really wound up with the ozone data very similar to what we would have expected going in. So as far as changes to how we handle the ozone, not so much, but the LVP-VOCs themselves and their availability through evaporation, certainly it looks like the barrier needs to move a little bit.
Thank you very much for your presentation. I do want to repeat that ARB includes consumer products in our inventory. The thing that I've worked in the consumer products section for a while, the thing that jumped out at me is when you compared different products, the lotion versus other products. And that gives me pause to jump in with the regulatory framework for certain LVPs because you have such a significant use parameter. For example, as you say, laundry detergent down the drain. You could also include shampoo, soaps and conditioners, similar thing where the neat compound or neat product may have a VOC, LVP-VOC contribution, but the way it's used would significantly reduce its impact. So that's where I would cause one to consider the formulation of the consumer product may have an overreaching impact on the solvent used in the preparation.
And, just to follow up on that, I just put back up the slide again showing two different consumer products with the same LVP present forming very different amount of aerosol. So looking at solely from the select LVP-VOCs, I would agree you have to be very careful in how you want to move forward, both from as final fate, you're just talking about down the drain versus getting to the atmosphere, and as well as it does look like, based on these results, you can't just pick on a couple LVP-VOCs, right? In here, this is probably the clearest case of anything we had, and that's one reason I wanted to show this slide is, again, laundry detergent, that is a lot of aerosol being formed in this case. That's 200 micrograms per cubic meter. That doesn't mean anything from a perspective, oh my goodness, here's where the air quality standard is. But it does mean a large fraction of the laundry detergent is converting to SOA, a much larger fraction than can be explained by 15% propylene glycol. So it is very interesting. There's a lot of questions out there. With the lotion, also just want to reiterate that the way that the lotion was formulated actually led to some of our, basically we did some additional chemical reactions. We didn't take a pure mixture. So forget the pure compound. Even the pure mixture is not really what the lotion is. And we know that, right? Lotion doesn't look anything like the chemicals that we put in there. We had to cook it. We had to cross-link some things. So I appreciate that comment.
Related to this question, I got some questions from South Coast AQMD. But before you answer those questions, I actually want to mention one other important thing you mentioned, which is the environment effect of those compounds. That's another study by UC Davis we look at. Because look at those two compounds we are listing here, the laundry detergent and lotion, for instance. The laundry detergent actually a significant fractions go down the drain, and based on other study, it's not really evaporated that much once it's down the drain. So that is other factor we have to consider, and it's actually the first question on the South Coast is, yeah.
So why was laundry detergent used as one of the main products of study, since there's a large down-the-drain effect for such products? Well, this is where I get to say that we had a large meeting with ARB staff and the consumer products agencies and AQMD staff, and these were the ones that were recommended based on their use and based on the type of chemicals present. I agree that laundry detergent, the way I use it, goes in the wash machine and down the drain. However, this is essentially was one of the consumer products that everyone really got together and agreed would be one of interest to study. I know that's not necessarily the most satisfying answer, but that's exactly why it was chosen. How do the ozone formation potentials of the LVP studied compare to currently defined VOC exempt compounds such as acetone, methyl acetate, etc.? I should note in here that this study itself, we were not expected, nor did we actually figure out the MIRs for any of the individual species. That would have taken some additional modeling work and was beyond the scope of this. So that's a very difficult one to answer. But what I can say is that since the models, the SAPRAC chemical mechanisms good fit to the LVP-VOCs that we studied, worked out very well, that the MIRs associated with these are probably pretty good. But I can't really make a direct comparison based on this study, other than to say that the experiments were conducted and modeled very well with the SAPRAC chemical mechanism, which is used to get MIRs and ozone formation potentials. And I've got, what are the implications of this work on CARB's LVP exemption considering the compounds studied evaporated and formed ozone and or SOA. Well, that's something I think we've been kind of touching on. The implications of this is sort of mixed. Right, we got a lot of different pieces to this puzzle here. We've got the one is its ability to evaporate if it's open to the atmosphere. One is whether it actually gets to have the time to be open to the atmosphere versus going down the drain. I think what it really gets to is that we have to look at how the LVPs are used, whether the LVPs are really the LVPs inside the mixture. Again, pointing down at the lotion here. As well as the information that we generated as part of this study. So, use, storage, these are all very interesting questions. Like I said, there's a companion project that looked at down the drain. So if you guys can they still see the slide? Yeah. Again, looking at the slide that's up, laundry detergent shows this huge amount of SOA formation, yet if you look at the down the drain factor, most of this is going down the drain. 95%, leaving 5% of it, which is still one of our bigger aerosol formers in the study. So, as far as the implications of this work, I think that the chief implications are, one, the LVP-VOC itself, the individual one, can't just be looked at by itself and assume that that's the big driver for the mixtures. I think you can't even assume that LVP-VOC is in that form inside the mixture. I think it's pretty clear that some of these chemicals that we assume don't evaporate do evaporate on if given a reasonable if given long enough to do. So I think I think you asked a very good question. I think there should be a lot of good conversations going on between the ARB staff, AQMB staff, and others on exactly what to do. But the ozone chemistry looks like it's okay for the LVP-VOCs we studied, and you should not assume that all the LVPs are forming tremendous aerosol. And I think that's neat. The last question I don't think is really for me. I think it's for my audience. It says, how does CARB intend to use this research? I don't have the answer for that. I think I look forward to finding out how they want to combine the information of this availability coupled with reactivity for ozone and SOA. I think it's a very interesting study to have looked at, and I think that that's going to be some good challenges for the ARB staff to figure out.
Well, I have one last question from the webinar, but this is actually a regulation kind of question. I will go to, if you demand, can you answer this? This is asking about how the regulatory, how the LVP-VOC being exempted.
Okay, let me just read the question. What regulatory vapor pressure exemption is the presenter referring to? Aren't consumer products regulated based on total hydrocarbon/VOC emissions, regardless of what the vapor pressure of the individual constituents is? So, yeah, the presenter is referring to an exemption in the consumer products regulation for low vapor LVP-VOCs, and there's a slide that the presenter is showing right now on the screen, and that slide has 3 bullets showing the 3 different ways in which VOC can be considered a low vapor pressure VOC. So it's based on the high boiling point and low vapor pressure and number of carbon atoms. And so as a practical matter, as regulatory staff, when we recommend to our board and our board sets limits for the VOC content of a given type of consumer product, that would be expressed as a VOC in the product. When we look at the formulation, we do not include LVP-VOCs as contributing towards that limit. Thank you.
Well, thanks very much, Trevor. Well, let's thank Derek again for a great presentation and also excellent work he did on this project. And thanks very much for the audience as well online and in the conference room. Thank you.
It's a good one.
Thank you.